you. Thank you very much for inviting me. It's very kind. It's a great honor to be here. I'm going to today give you a little bit of a, as I say, a personal perspective, a little bit of a historical context to what I've been working on. I'm very old, as you can see, so I've been working in solar physics for many generations. And then I'm going to bring you right up to date with what we're working on. Officially, I retired in 2017, but actually I've still been quite busy, both with research and outreach. So I'll come to that towards the end of the talk. I'm at the Department of Applied Maths and Theoretical Physics at the University of Cambridge, and I also hold what's called an STFC Leadership Fellowship. That's for outreach, for working in outreach. So we're not alone in what we do, and I've had the honor and the pleasure to work with a very dynamic team of people over the years, and here's quite a few of them. Some are now scattered around in the USA. Peter and Steve are over in the USA, and Steve's student. Here, Jeff and Durgesh is back in India, and I still continue to work closely with Durgesh and his team in India. And Sargam, who did a PhD with me, is now up in Glasgow working with Lindsay. Vanessa is also another PhD student, is now over at Lockheed working with the IRIS team. And Julio, of course, has been with me for many years and features in quite a lot of the work that I'm going to talk about today. Julio and I have worked together for many, many years, and he's now head of the group at Cambridge at the Solar Group and Atomic Physics Group. So, eclipse of the sun, many of you will recognize, and I can see Shadia is here as well, and she will certainly recognize. One of the most stunning experiences you can have, absolutely awesome. And not just from the perspective of seeing the corona, but also from the environment around. I've had the honor of experiencing 3 total eclipses of the sun. Well, my career started back in University College as a PhD student with Professor Mike Seaton, who you can see sitting here, very famous atomic physicist, astrophysicist, and he's talking there to Alan Burgess, who was a key person with the development of dielectronic recombination, which is a process which is very important in the solar corona. And when I asked Professor Seaton about doing a PhD, he said yes, he was interested, and what he did was to give me some eclipse observations, and said what he'd like me to do is to work on the visible lines, visible coronal lines. So in the Atomic Physics Group at University College, people were working on several different aspects of applying atomic physics to astronomy. So I was asked to work on the 1952 eclipse, and that was a very good eclipse in the point of view of the observations that we had, the spectra that we had from it, taken by Leo, who was a fantastic observer and built a special instrument to observe the eclipse. And what I was asked to do by Professor Seaton was to do atomic physics calculations, which would enable us to analyze the visible lines that we see during a total eclipse of the sun. Now, it took astronomers quite a time to realize what these lines were due to, the red line, the green line, the yellow line. And it was based on some very careful laboratory work by Edlen over in Lund and Gretchen, that they were able to identify those lines. And he extrapolated the laboratory spectrum, but it took a long time and a lot of very careful laboratory work. And sometimes laboratory work is underestimated, and it's very important in atomic physics and particularly in the sun, because sometimes we can't necessarily reproduce the conditions on the sun, so we need to depend on laboratory work in some ways, fusion research and things like that, to be able to identify some of the lines or to be able to analyze them. So the red line is due to a transition within the ground configuration of iron 10. And the green line is due to a transition within the ground configuration of iron 14. And these high ionization stages, iron being having 13 electrons stripped off, meant that the temperature of the solar corona was very hot. It was 1,000,000 degrees. And this was unexpected, and that's why it had taken a long time to identify these lines. And it was also important at that time, as I say, the work that Alan Burgess and Mike Seaton did on recombination and ionization to determine at what temperatures those ions were formed. So what I was expected to do was to do calculations, but when you do calculations for these transitions, you can't just take those two levels that you see there for iron 10 or iron 14. What you have to do is to take many, many levels in the iron and look at all the processes. So we had to look at the main processes, which is electron excitation up to excited levels and then radiative decay down. And I did the first calculations of any accuracy for many of these coronal ions using atomic physics codes that had been developed at University College over a period of about 10 years. So other people had been working on these codes and I applied them to the coronal ions. We used a relatively simple calculations at that time. And I just wanted to show you the sort of tools we had to help us in those days. And, you know, we're now up to doing 3D, MHD simulations, et cetera, et cetera, et cetera. But basically I was working with cards. When I first started, it was punch tape, carrying boxes of 2,000 cards up and down 3 sets of staircases, and then finding that one of the cards had been duplicated or something wasn't quite working right. So we used computer punch cards, we used slide rules, we used log tables, and some of you that might be of a similar age to me might remember some of these. It was quite laborious, and the power that you have now in your mobile phone exceeds the sort of computing power that we thought was unachievable in those days to run these calculations. So that was a piece of work, and we then analyzed the observations from the 1952 eclipse, and we got some interesting results and abundances, which again, I'll come back to abundances, but the coronal abundances are somewhat different in active regions, and particularly in the core of active regions, than they are in the photosphere, the FIP effect. And we found that with the observations from the eclipse. And because we had continuum, we were able to get absolute measurements for some of those elements as well, calcium and iron. But when I'd completed the work on the visible, sorry, went too far. We moved to the ultraviolet. Professor Seaton decided it was time for me to move to higher energies and to work with colleagues over in the USA. We also had colleagues at the Cullen Laboratory who were analyzing the spectral lines. And so I went over to the USA to work with colleagues at Goddard and Naval Research Laboratory. But I also started working on some Skylab's observations. And I wanted to bring this to the attention of some of the younger members of the solar physics community, because there are three volumes, and Skylab had some amazing instruments on board. Here's a picture, a photo from the X-ray telescope, and you can see the coronal hole, and that was the time in which they were able to link the coronal hole with the fast solar wind. You can see a very nice equatorial coronal hole stretching right down there. But there were several different instruments, and there was a whole series of workshops which were very, very useful, very interesting, because it brought people together 3 times to sit to work on particular problems. And I was honored to be able to participate in the workshops on solar flares and the workshop on solar active regions. And each of these led to a volume of very interesting papers. So there in the bottom left is an image from one of the instruments for the Naval Research Laboratory called SO82A, which is affectionately called an overlapogram. We were able to use these spectral observations to get densities. I worked a lot with Ken Deere, and we were able to, on the left-hand image there, you can see electron densities from diagnostic line ratios as a function of temperature for a small compact flare that we were able to obtain. So with this overlapogram, which had overlapping spectral images, we were able to look at compact regions quite well. And down the bottom is a spectrum, and you can see many of the interesting spectral lines from it. I also worked a lot with George Doshek, and we worked on solar flares and the solar flare workshop. And there you can see we not only studied the solar flares, but in those good old days, we actually we also wore flares as well. So that's a picture of me and George when he visited us in Cambridge many years ago. We not only studied compact flares, we also studied larger two-ribbon flares. And one of the interesting lines that George and I were studying was the iron 21 line, which is at 1354 angstroms, 1354. And this was seen with another instrument from the Naval Research Laboratory. And it's been a line that I have studied throughout my career. It's a very interesting line because at that longer wavelength, you're able to measure its width, and you're able to do many things with it. And you can see you can got chromospheric lines there, so you're actually able to measure velocity shifts very accurately for the iron 21 line. It's formed at a temperature of 10 million degrees. So a very interesting temperature for flares. The next set of space observations, solar space observations that I worked on was from the Solar Maximum mission. And this was tremendous opportunity, a really good satellite, and it had instruments in the ultraviolet, the UVSP, and in the X-rays. X-ray polychromator, those are the two instruments I worked on. It had a lot of other instruments in hard X-rays and various other instruments. But the X-ray instrument had a flat crystal and a bent crystal, and we were able to observe lines at very short wavelengths. There you can see a chronograph image. It didn't see the whole sun, but it had a quadrant of the sun, but some very beautiful and interesting observations from that too. The aim of a Solar Maximum mission was primarily to study flares, which is what we did. But since it was Earth orbiting, inevitably the flare happened when it was around the back of the sun. So we would come in the morning and there would have been a flare the previous night. So the aim was to try and catch it early on. And we were able to do some interesting work with the Solar Maximum mission. One of the things that was studied a lot by many people, Esther Antonucci and many other people, was the blue shifts that were seen in some of these high temperature lines. And this was interpreted as an indication of what we call chromospheric evaporation during the flare process. In which the electron beams hit the photosphere, and then you get material evaporating up, which is high temperature. And this is a process that we've studied more recently with iris observations, etc. But it's the X-ray polychromator didn't have a very good spatial resolution. The FCS had a spatial resolution of about, I think, 15 arc seconds, but the BCS, which sees the very short wavelength X-ray lines that you can see here, it didn't have a spatial resolution. It was mostly a very large field of view. So it wasn't clear where those blue shifts were coming from. And one of the points was we wanted to identify where the blue shifts were coming from. I did some work with the UV instrument with Dick Shine and Joe Gurman and Richard Harrison, in which we were able to locate the position of these blue shifts using the iron 21 line, which I've just mentioned. The UVCS covered that wavelength range. So we got a lot of interesting observations with the iron 21 and for other lines as well, for transition region lines from the UVCS instrument. One of my wishes is that some of this data was still readily available with the software to analyze it, because the frustration was, at the time, we saw some really interesting observations, as you can imagine, but we weren't necessarily able to put them into context. And now that we know a lot more, and we've had higher spatial resolution observations, and we know a lot more, it would be really interesting to go back to some of the observations we saw then, or some of the data we had then, with a new perspective, the perspective of what we know now. There's still a lot of a very rich amount of data there. Another instrument that I wanted to bring to your attention that younger members of the solar community might not be so aware of is a spectrometer called Hertz. And this was had a stigmatic slit, and also had a spatial context. A very good instrument, which was flown on rockets, and also, as you can see here from this picture, was flown on the International Space Station. And Gunther Bruckner was the PI for that instrument, and I did a lot of work with Ken Deere on line shifts and on line widths for the transition region lines. We saw a lot of energetic events, and there's several papers that we did relating to that. Being a rocket flight, of course, it was quite short in its time, and it in those days, this was taken with photographic plates, so it was quite difficult to analyze in some ways, but it had a very good dynamic range. And I do believe that some of these plates were digitized, although I'm not sure whether they're available now. I know there was a program to digitize them all. So moving on to more recently, only 20 years or so ago, was SOHO. And SOHO was an amazing satellite. I think it's probably one of the best, most comprehensive solar satellites that we've had. And it's, of course, still operational. Not all the instruments are still used because they've now been superseded. But the satellite is still operational. We did lose it for a little while, just after launch, or not long after launch, a few years after launch. And we were fortunate enough to be able to find it again with the Arecibo telescope, which has sadly now met a rather sad end to its life. And enabled to bring it back to life, to thaw it out and thaw all the instruments out, which was very exciting. But as I say, it was possibly the most sophisticated solar observatory that we have, and it was at the Lagrange point. So it was able to see the sun, and is able to see the sun 24 hours a day. It had instruments on it to study the solar interior, the solar atmosphere, the solar wind, and my particular interest was in the solar atmosphere and working with the instruments that were being used to study the solar atmosphere. It was operated from the Goddard Space Flight Center, and it was very exciting. The Solar Maximum mission was also operated from Goddard Space Flight Center, and it's very exciting to work with a team of people. And we were able to decide, what we wanted to study together with all the other members of the instrument teams. So basically, I think that each instrument is useful and unique, but much more is learned when you combine different instruments together. I think that's what we've learned, particularly when you're using a spectrometer, because you really need to combine it with other instruments. A spectrometer is quite slow as it scans, But if you combine it with an imaging instrument, then you can see much better what you're observing. So a lot of the work we've been doing in our group is actually combining several different, the data from several different instruments together. So the instrument that I was primarily involved with was the coronal diagnostic spectrometer. And this is an instrument which had a stigmatic slit. That means you get a spectra at each position along the slit. And in order to build up an image, you have to raster across that image. So it can take some time to raster across an image to cover a particular area. You have many choices of different slits to use, or different exposure times. And sadly, as it was with other instruments that worked, you're not able to necessarily bring down all the data that you have up on board the satellite. So I liken it to having a group photo, and you've got to decide, whether you bring down one person's arm or one person's foot. You can't bring down all the data that you have. So we had to write observing programs which are designed for specific scientific tasks. So if we want to have a scientific objective, then we decide which spectral lines we want to use, how long we want the exposures to be. Now, this was slightly different in the days when we had photographic plates, for example, on Skylab, because we could just bring down the whole spectrum on the photographic plate. So, that was one of the advantages of being able to get that data back. So I worked on CDS even before launch in the design of the instrument and what wavelengths we wanted to focus on, and also working on the software for the instrument. And it's around about that time that we decided we needed to have a package which would make accessing the atomic data easier, because previously, if you were looking at a particular ion or a particular spectral line, you'd have to go and look up all the papers that you needed to work out what the intensities of the line were as a function of density or temperature. This is a laborious task. So Ken Deere, myself, and Brunella Monsignori-Foissy got together at a solar physics meeting one day over lunch, and this is something we're really missing at the moment. Is not we get the meetings and we get the talks, but we don't meet together over lunch and at other breaks to discuss how we could collaborate. And Ken at that time was doing, I think, a review of there was a series of books with lots of atomic data in, and he was doing a review, and he said, well, why don't we put this into an electronic form so that other people can use it as well. So that was when we founded the Chianti Atomic Database, and we wanted to review published data for different atoms and ions, and bring in all the data that was necessary to calculate the spectral line intensities. And that was quite a large task in itself, but we also wanted to assess that data. So we didn't want to just use any data. We wanted to make sure it was complete. We wanted to make sure it was consistent. And we did that using a method that was developed by Alan Burgess to present the data visually so that we could see if it was converging to its high energy limit or its high temperature limit. And we could see if there were any inconsistencies in the data. And it was amazing as we started to go through the data, how many inconsistencies we did find. And then we'd go back to the authors and we'd check up on it or compare it. So the idea was not just to assess data, but it was to have bring the data in that we considered to be reliable and was the most recent. Sometimes there were lots of gaps in the data, and we also needed to fill those gaps by doing new calculations. And we did new structure calculations and new scattering calculations. So here is the members of the team, and myself and Giulio Delzana, Enrico Landi, Ken Deere, and Massimo Landini replaced, sadly, very, very sadly, Brunella died far too young, prematurely. Actually died sitting at her desk doing a calculation. Very sad. And Massimo replaced her on the Italian side, and Peter Young, there, who was my research student at the time. So we wanted to make this data freely available for everybody to use and to keep it updated over the years so that it would be a resource. And it has been a huge resource for solar physics, not just for spectra, but actually also in building instruments, because you can use it to predict what the spectral lines will look like, and also for imaging instruments, because even with an imaging instrument, you need to know what temperature the different channels are responding to. And we've done a lot of work in investigating, for example, with AIA, what spectral lines are contributing to various channels for different types of regions, and therefore what the temperature response actually is and what we're actually seeing. So just very briefly, the intensity of a line is a function of the abundance there. This G of T, which is a function of the atomic physics parameters, electron density squared and integrated along the line of sight. So this G of T is a function of some constants, Planck's constant, speed of light divided by the wavelength, the atomic transition probability divided by the electron density. The next term there, Nj over N, is the population of the level J. And then Nx plus M over Nx is the ionization balance, so the ionization ratio. Now, very often in equilibrium, we consider that the population of the ion and the ionization balance can be separated and that they're independent. That's not always the case if we're looking at something which is time-dependent ionization, for example. So basically, the G of T function is something we calculate with Chianti using the best atomic data that we have for the population of the levels inside a particular ion. And we bring in the ionization balance. So the intensity can be expressed in terms of the integration of the electron density squared if we approximate, and that is the emission measure. It's the amount of, basically the amount of material at different temperatures. Now, I'm not going to go into the details of the diagnostics, those are described elsewhere, but we can also use line ratios to get electron density. We can do various other things. Here's just a comparison of the prediction of the Chianti spectrum with the CDS normal incidence spectrometer. So of course, not only do we calculate this data with Chianti, we do a huge amount, and Giulio has done a huge amount of this, of benchmarking, of checking it against laboratory wavelengths, laboratory intensities, checking the intensities against solar spectra, against stellar spectra. One of the things excuse me. One of the things I did with CDS was I worked very closely with Dave Pike, who's also now retired. And this is one of the papers I wanted to bring to your attention. And this is looking at filament, a flux rope ejection in oxygen 5. Perhaps, very early observation of this. And we were able to determine the speed and also the rotational velocity as it came towards us. And it's always interesting and always good to get press releases. And here we have a press release. On the front page of a tabloid, space storm that could paralyze the world. So, it's good to get press releases, but don't expect them always to be scientifically accurate. In 1998, I was privileged to be able to observe a total eclipse in Guadeloupe, an amazing experience. And here's the privilege also was that I was with many of the solar colleagues. We had a solar meeting there and we were able to experience the eclipse. So many people there, Ken, Dear, Jim, lots and lots of friends and colleagues were able to experience it together. Hinode, I worked with the team spectrometer on Hinode. Here's Louise Hara, who was the PI on the ICE experiment. Hinode had several different instruments which were designed to study the solar surface and the interaction with the solar atmosphere, both the ICE EUV spectrometer and the X-ray telescope. So we did a lot of work with ICE. Again, it was a scanning instrument, so it had a stigmatic slit, it had different slits, and it could scan across a particular area, getting a spectra at each position along the slit. Spectral instruments are quite difficult to analyze, and software has been written and there is documented. Peter Young's done a lot of this for ICE to help people to analyze the spectra, and here is the spectra you can see from ICE, which is dominated by many iron lines and many other lines. So we have a huge amount of information there. I rather like this. This is iron 15 on the left-hand side in solar minimum and iron 15 in solar maximum. I've forgotten who put this together. I think it was, should have credited them. I think it might have been Harry Warren or maybe David Brooks. And on the other side, you can see solar minimum in 3 cooler lines. The blue is silicon 7, iron 12, and the red is iron 15, during again solar minimum and solar maximum. Rather beautiful and very scientifically interesting. But as I say, we can take ratios of lines and get electron density determination from it. And here's a ratio of iron 13 lines. So the ratio is on the y-axis and the log of electron density on the x-axis. And then we can see from the ratio of 2 lines, in this case it's 2 iron 13 lines, we can then determine what the density is, and we can make density maps for different regions, which gives us a lot of information. This is an active region that one of his former student, Brendan O'Dwyer, looked at. You can see the limb of the sun, and you can see a temperature map and an electron density map for this active region. So very hot and very dense, low down in the core of the active region. We've done a lot of work over the years with loops workshops, which happen every 2 years, trying to match up theoretical models for the heating of coronal loops with what we observe from the emission measure structure, the slope of the emission measure at low temperature and high temperature. We're making a lot of progress with this, but there's obviously still a lot of debate, and we're hoping to have another meeting next year. One of the models proposed is Parker's model for nanoflare heating of coronal loops, in which the strands that are within the loop get twisted up, and then magnetic reconnection happens in these strands. And this has been tested out, and a lot of models have been developed by various theoreticians over in the States, Jim, Peter Cargill here in the UK, and Steve Bradshaw and Harry and other people are now doing models to try and simulate what we're observing. Another feature of the ICE observations is the red and blue shifts that were very prominent in the data that we obtained. So here is iron 12, formed about 2 million degrees. And you can see the red and the blue shifts, and the red is material condensed moving away from us, and the blue is material moving towards us. And there's been a lot of debate and discussion as to how these red and blue shifts are formed. The red is probably condensation within the loops, and the blue could be material coming out towards into the solar wind. But another process called interchange reconnection has been discussed and developed. Giulio and colleagues over in France proposed this happening above an active region from the data they analyzed. And this would take material into the solar wind. And he also worked with Steve to look at what form this material would take, how it would be heated. So this interchange reconnection, I think, is still very relevant in our recent observations with Solar Orbiter, trying to understand the connection between the active region and the slow solar wind. The fast solar wind we know comes from the coronal holes, the open regions, the coronal holes. And I did some work with Don Hassler about that with the SUMA instrument on Soho, identifying where we thought that this fast solar wind was coming from. But the source of the slow solar wind, which is more intermittent and bursty, is more difficult to tie down. And there's a lot of current debate still about its origin. Another area that we've worked on is with sigmoid, the emergence of flux, and then the eruption of coronal mass ejections, of prominences. And this is early work we started with Sarah Gibson when she visited Cambridge for 2 years, and worked with various other people, with Julio and with Durgesh Tripathi here, using CDS observations to look at the temperature structure of this sigmoid structure. The sigmoid structure indicates that an active region is going unstable as the magnetic field gets twisted up. It was seen first of all in X-rays, so it's known to be quite hot. But just recently, I just wanted to mention that we've just published a paper, it's just been accepted, led by Sargam, looking at this very high temperature emission. So this is using SDO observations, but you can see there, the red there, those are strands of very high temperature plasma around about 10 million degrees within the sigmoid structure. So we're actually looking at flaring within the sigmoid structure. So a series of flares that happen, small flares that happen during the formation and development of the sigmoid structure. So bringing that right up to date. The IRIS observations. IRIS is again a spectral instrument, a really excellent spectral instrument, which has a context. So you can see where the slit is relative to spatial context in one instrument. So there's no doubt about that. It's looking primarily at the chromosphere and the transition region lines. And we've been working on various projects with the IRIS team, both at Harvard here, with Harvard, but also in Lockheed, where Vanessa now is. So here you can see the sorts of lines that are observed: silicon 4, oxygen 4 in the wavelength band about 1300, 1400 angstrom. And we can use these for diagnostics, and we have been using these for diagnostics for a very long time, back in the SMM as well, the UVCS. And it's evident that the transition region is very dynamic, and the lines are broadened and they're shifted. But also, in addition, Vanessa was able to study the iron 21, my favorite line, this very high temperature, 10 million degree line, using the spectrum from IRIS, and she was able to locate the chromospheric evaporation in the footpoints of the flare structures. So some very, very interesting work by Vanessa using these iron 21 line, which pleased me a great deal. But also she was able to study the oxygen 4 lines and find very high densities. So very high densities, around about 10 to the 13 per centimeter cubed again, during solar flares. So indicating that the plasma is coming from low down in the atmosphere. I say a former student, Sargam, for her thesis work, did a huge amount of work on jets, which I just wanted to bring to your attention. I'm going to move a little faster because I'm running out of time, I think. She's published several papers on this. And again, I think jets are very relevant now because we see some features like the magnetic field flashbacks or whatever, that are seen with Parker Solar Probe. And again, the jets go out into the open field, so they could contribute something towards the slow solar wind. So I think jets are a very interesting feature to look at. They're very small, but they do link up into the open field. So coming up to date, more up to date, the most recent release of Chianti 2021. I've stepped back from Chianti a little bit. I'm not playing an active role now. I do keep my eye on it, but it's mainly Ken and Giulio, Enrico and Peter that are now updating the Chianti and producing modifications for it. It's been hugely successful. You can see the citations there, over almost 4,000 citations, and it's being continuously updated. So the latest edition was in 2021, a new edition is coming to it. It requires a huge amount of atomic data, and a lot of that atomic data has been fed in from a project in the UK called APAP, which is led by Nigel Badnell up in Strathclyde. And again, I was very much part of that, but have stepped back a little bit from that now. But they're continuing to progress, doing new calculations, updating calculations, and the information is available there. I wanted to also to mention the student Roger, who is working with Giulio now, and he's been doing some very interesting work on a collisional radiative model, which brings together the model of an individual ion with the ionization and recombination to look at density effects, which can significantly change the ionization ratio. There's the picture there is the oxygen ionization ratio comparing Chianti, which is in equilibrium, with a higher density new model that Roger has been working on, but also including many other processes, photo excitation, photo ionization, and charge exchange. So he's just completing his thesis and has published several papers already, and more to come on that particular work. I also wanted to bring to your attention the review that Giulio and I did recently. It covers a wide number of topics, as you can see just detailed here. I won't run down them all because I'm running out of time, but I do urge, if you're starting out in the field, if you're young and you're starting, do have a look through that. You might not want to sit down and read it. Even we don't want to sit down and read it, but you might want to dip in and out to different sections because it is a very comprehensive review. And I can tell you it took a huge amount of work, particularly on the part of Giulio, to put it together. So it's a good starting point if you're interested in pursuing particular areas of diagnostics. I was very, very fortunate recently, returning to eclipses that I love, to be able to participate in the eclipse that went right across the USA in 2017. I was invited to be the NASA solar expert at the Great Smoky Mountains National Park, which was a real joy, and it was a completely different experience. I also experienced an eclipse in the UK in Alderney, which was again a different experience. But here I wanted to show you the Cherokee Indians. We had a big celebration. We had stories, dance, we had all sorts of things happening, people from Marshall telling us about Earth observations. But here is you probably know the legend in the Chinese of the dragon eating the sun. Well, the Cherokee Indians believe that a big frog eats the sun. So I was a little bit nervous there about meeting any big frogs. Here is a very beautiful, and Shadia will recognize this one. This is a very beautiful coronal image, putting together the spectral lines from iron 14, the green line, with the red line. And you can see the detailed structure there and the interesting observations and science that's built in there in the temperature for the red line and the green line. So very quickly, I just wanted to update you on what we're working on now. We're working with the team in Harvard. Now, Jana there is leading the project, which has been, it's called AirSpec, and it's been flying high-flying aircraft during eclipses. They've flown during 2 eclipses so far, I think, 2017 and 2019. And what they're trying to do is what they are doing is getting spectra in the infrared. Why are we interested in doing that? I'm almost finished, Maureen. Are you interested in doing that? Because these infrared lines could ultimately be used to measure the magnetic field. And if you go high enough in the atmosphere, you can observe them during the eclipse, and we can get a lot more information. So we're using them for diagnostics. This diagnostic is taking the ratio of 2 lines to get a density down in the bottom right-hand corner. This is not published yet. This is something we're working on, and we're comparing those densities with, for example, densities that we get lower down in ice, etc. It's also possible, perhaps, to get abundances as well. DKIST, obviously I think many of you are aware of it. Fantastic observations that it's getting already in the for the photosphere chromosphere, but also eventually it will have coronal observations. And again, in the infrared, the iron 13 lines in the infrared can be used to measure magnetic fields. So very exciting to use those observations and to get those observations. In order to prepare for that, we've just published a paper. This is a recent paper with Yarrow. We've done a huge amount of work with Yarrow and his group on non-Maxwellians. I don't have time to talk about that at the moment, but what we're doing here is comparing temperatures for the infrared lines from COMP densities from the infrared lines from COMP with densities that we obtain from ice. And we get very good agreement between the densities that we obtain for those two. That's now published, so you can check that one out. I mentioned Solar Orbiter, and I will mention Solar Orbiter because, of course, it has a spectrometer. And one of the interests in solar is connecting the source region on the sun with the solar wind. And there are various models that could be possibly linking it. And one of the hopes is that we can use something very special, the element abundance variations, to actually trace from the source into the solar wind. Many things change, like densities and temperatures may change as they progress into the solar wind, but the abundances don't change. They're like putting a trace ink into a flow from the source region. It doesn't change. And there's quite a lot of work going on in that regard. This is a spectra from the first results from SPICE, the SPICE instrument connecting with other solar wind instruments that are sampling element abundances. So that's something for the future, not necessarily for me, but for other people who are younger than me to work on and take interest in. Julio's just published a paper. It's just in its proof stage. It will be available very soon, on the potential of the X-ray wavelength region, in particular the potential of the region around about 100 to 150 angstrom. And here's a comparison with a very old spectrum. There's very, very few spectrum. In the X-ray wavelength range has been a little bit neglected in solar science recently, but this is an OZO 5 spectrum that I worked on many years ago, and there is potential there in that X-ray wavelength range, not only for active regions, but also for microflare observations. And as I say, that paper, a very comprehensive paper, is just available. One other group that we're working with is the group in India. And they have an instrument, this X-ray solar monitor, on Chandrayaan-2. Now, obviously, Chandrayaan-2 is orbiting the moon, and it's looking at the moon, but it's looking at the solar spectrum to compare with the fluorescence from the moon. So we're doing some very interesting work with colleagues over in India in the Physics Research Laboratory in Ahmedabad, and couple of papers have been published already, but we're seeing small microflare events, even when the sun is very quiet, even when during the minimum of the sun, we're still seeing these small microflaring events, and they are able to analyze those, get information about those from the diagnostics. They have spectra, they can fit, get abundances. So some very interesting results coming out there. Something we're looking forward to in the summer is the launch of MAGIX. And again, it's a project we're involved with. And this is a project led by Sabrina and Amy Weinberger in Marshall. And this will look in the X-ray wavelengths range, around about 10 to 15 angstroms or thereabouts. And it will see these high temperature lines, and we'll be able to do studies on active regions to tie down the heating mechanism for those active regions. So I've almost finished. I'm just about saying we're working with people in the States. There's Dergish's group now. He has a very big group in IUCA in Pune, and we're working with them. They've got a satellite called Aditya, which is being launched in the summer. I think it's in the summer this year, and that will be at the Lagrange point, and that will have some very interesting instruments on it, coronagraph, chromospheric instruments, etc. So very exciting to collaborate with that. I've been working, besides the research that I'm doing, I've devoted a lot of my time in the last 5 years to outreach, and I've just released this summer a site called Sunspace Art, and the project brings scientists and artists together to work with school children. We've been working a lot with younger school children and producing some amazing art. So that's taking a lot of my time. We had a STEAM festival, that's STEM plus Arts, in February online, which is on YouTube, you can see it, a lot of exciting work. So all in all, I just wanted to say that had a wonderful several decades in solar physics, working with colleagues all over the world, and both on research projects on solar satellites and also on outreach work. So it's been a lot of fun. So there we go. That's the end. Thank you.